All right. This is going to be a filler for my mistake. For Chem102. And in reference to exam number 4 on chapter 14 and 15. Actually, this will only be chapter 14. Review on acids and bases on the 30th of June. And this will be a portion of the review that I forgot to record. I started the recording late, which means I got to go back and fill in the first part of the recording with the questions that were reviewed at the time. And I'll do that in just a second. Let's see, I'm going to pause this thing. Okay, I'm back. So this is going to be chapter 14 only. And I'm going to go through discussion of review document for chapter 14, problems 1 through 9. I think we skipped one of them in there, but I'll just do them all. Let's see. So hold on a second. I want to not be interrupted by any intruders. I'm going to lock the meeting. There we go. And we'll begin with problem number 1. Okay, which of the following is a conjugate acid-base pair? Remember the definition of an acid dissociation. And for convenience, we're going to leave out water. We're going to use the dissociation mode only, and not the transfer of a proton to water to make hydronium. So you get the proton and there. So you have the acid and then the conjugate base. Right? What do we know about those two in relation? The conjugate acid-base pair is this one and that one. Right? So you'll see it in this problem. It's that one slash that one. First thing, you got to have an acid, right? You have to have one with a proton that will dissociate. Right? Then the conjugate base is the result of losing one proton. Right? One proton there gives you that acid. What if we have two? Say we have two acid protons in that molecule, a diprotic acid. In that case, you lose one proton and you still have one attached. That's an acid-base pair. Right? The other possibility is, suppose you have a, we'll talk about that in a minute. Let's look at our choices. So our choices are this one, this one, and this one, and this one, and then more than one. There we go. All right. So they have to meet two conditions. Notice that the A is common on both sides. So whatever A happens to be, It could be an element, an ion, or it could be a polyatomic ion, right? But in any case, if it's over here, it's got to be over there. All right, that's second condition. First condition is you have to have the dissociable proton, and you only lose one at a time. But you also have to have that part of the molecule on both sides. That's the common ion for both sides. Okay, so we've got this acid, hydrochloric acid. It's got a dissociable proton, and then they're saying the conjugate base is OCl minus. Right? Cl minus over here, OCl minus over here. It's not a common ion. That's a different anion than this one, right? So that disqualifies this one. How about sulfuric acid, H2SO4? They're saying in this example that SO4 minus is the conjugate base of this acid. It's not, because you've lost 2 protons. The conjugate base would be losing 1 proton, right? So that one's wrong. How about this one? Well, ammonium ion has a proton that can dissociate, and when it does, it gives you this conjugate base. That's true. But since E says more than 1, we have to go to the next one and be sure either it's true or false. All right, so the hydronium ion can lose a proton, right? It's an acid, technically speaking. But what's left over after you lose that proton? Water. So this would be water if that were to be true, right? Consequently, it's false, false, false. The only true one is C. All right, that's number 1. Let's move to number 2. All right, number 2. The hydrogen sulfate or bisulfate ion, this, can act as either an acid or a base in water. Okay? Which means, according to Bronsted and Lowry, since this is aqueous solution, it can either give up that proton or it can accept a proton from water and make H2SO4. Okay, so that's given. The question is, in which of the following equations does HSO4 minus act as an acid? So if it's going to act as an acid, it must dissociate by releasing that proton. Okay, that's the acid reaction for the bisulfate anion. Now all you have to do is look down at your choices and see which one matches. Well, okay, we've done the dissociation here. The choices in here look like they're using water somehow. So what would the water look like? It'd be like this. Like that. Okay. And the one that fits that description sorry. I transferred a proton from here to here. So that makes this one there. If this is going to act as an acid, it has to give up that proton to water. There you go. So this one is D. That's number 2. Number 3. Number 3 says, which of the following is the equilibrium constant expression for the dissociation of the weak acid HOCl? So if it says equilibrium constant expression for the dissociation, that typically means don't put the water in there. So this one is what? Hypochlorous acid. Right? So the acid dissociation constant is this one, that one here, just like all our equilibrium expressions, and this one. Right. So now you have to do is just look down here and find the one that matches. And it looks like A. A matches. That's number 3. Number 4. Let's see. Well, which of the following is not true for a solution at 25 degrees centigrade that has a hydroxide concentration of 2.5 times 10 to the minus 6 molar? So we're given the temperature, and we're given the hydroxide concentration equal to 2.5 times 10 to the minus 6 molar. Okay. Which one is not true? Right. So we've got answers for each one of them. That means only one can be not true. The rest are true. So let's see. Is A true? Kw is equal to 1 times 10 to the minus 14. Is that true? Actually, all aqueous solutions possess that equilibrium constant. Anytime there's water in there, that one is there. Now, sometimes it's insignificant. There are other reactions that are more important, but it's still always there. So that's true. B, the solution is acidic. And C, solution is basic. Why did I put those together? Because they can't both be true. If we find the answer to one, we answer the second one. So let's look at this one. Is it acidic? Well, you could calculate the pOH and change the pH and say, okay, I know what the pH scale is like. Is it less than 7? But if we want to find out, is it acidic or basic, compare it to its neutral value. What is the neutral value for hydroxide concentration in water? Pure water, the neutral concentration of hydroxyls is equal to 1 times 10 to the minus 7 molar. So if we find a solution that's greater or higher concentration than this in hydroxyls, the solution is basic. Right? So the actual concentration is this, 10 to the minus 6th. 10 to the minus 7th is neutral. We have a basic solution. Right? So that one is true. This one is true. This one is false. So we found our false one. Right? We could look at the others. Hydrogen ion concentration is 4 times 10 to the minus 9 molar. Well, how do we find the hydrogen ion concentration if we know the hydroxyl? We have this expression. Remember, the Kw is this, and that's equal to the concentration of hydrogen times the concentration of hydroxyl. So we plug this value in here, solve for that one, and we get this one. That's true. And E says Kw is independent of other solutes. Actually, any solutes, not other solutes, any solutes. Right? Because water is going to be the solvent. Put anything into it, anything else is going to be a solute. That's true. Kw is there no matter what you do to water. It's always there. All right, that's number 4. And moving on, number 5. Let's see, I'm going to erase some of this in case I need the space. There we go. 5. All right. HA and HB are both weak acids in water. Weak acid. HA, HB are weak acids. HA is stronger than HB. So if HA is stronger than HB, that means the Ka of this one, let's do it this way. The K for HA is greater than the K for HB. Right? That's true. So now we have to say which, if any, A through D are correct. And then if none of them are correct, then we choose E, because it says A and D are all wrong. So if we find one that's correct, then E's wrong. So let's see. What about A? A says that A minus is stronger than B minus. Let's just look at that at the beginning. Is that true? If HA is stronger than HB, that means A minus is weaker than B minus. They're converse, right? The weaker the acid, the stronger its conjugate base. So if this one is weaker than that one, it's stronger than that one relative to its conjugate base. Right? So we don't have to go any further with this one. That one's false. Okay. B minus is stronger than A. Yes, that's true. So now we have to go to the next one, which is also stronger than water. Is that true? In most cases, yes. If you have a weak acid dissolved in water, then its conjugate base is going to be much stronger than the water molecule as a base. Now, that's not talking about OH minus. OH minus is probably, well, not, it's very strong, let's just put it that way. So, in most cases, since we don't have the K values available, this is probably true. These are both stronger than water. And also stronger than that. So chloride ion comes from hydrochloric acid, which is a strong acid, which means chloride ion is a very weak base. So that ratio is true. We found one that's true. So that's your answer. And in the interest of time, I'm going to stop it there and move on to number 6. Okay. Number 6, a solution in which the pOH is 12.1. So we're given pOH is 12.1. Would be described as what? Very acidic, slightly acidic, neutral, very basic, or slightly basic. Okay, let's take neutral first. What do we have to have to be a neutral solution? pH is 7, which means the pOH is also 7. Why? Because pH plus pOH is equal to 14. So if that one's 7, that one has to be 7 also. So C can't be right. So it's either acidic or basic, and then we have to decide how much. So now it might be worth converting pOH to pH, because we have a better feel for pH than we do for pOH. So what would the pH be? 1.9 pH. I'd say that is very acidic. Because what does it take to be corrosive? I think less than 2.5. So there you go. That's very acidic. All right. That's number 6. Move to number 7. This might have been the one I skipped last time. 7 or 8 I skipped. But that's okay. 7. I think I did skip this one. Which of the following indicates the most basic solution? So we're looking for the most basic. So we got to compare apples. If we've got apples and oranges and grapes and watermelon, got to change them all to apples in order to compare them, which is the most basic. So if A is a hydrogen ion concentration of 1 times 10 to the minus 10, pH is equal to 10, right? Negative log of that value is 10. Okay, so what's the next one? pOH. pOH is equal to 6.7. pH is equal to 14 minus 6.7, which is equal to 7.3, I believe. Okay, so that's more acid. So we're still, A is still more basic than that one. How about C? The hydroxide concentration is equal to 7 times 10 to the minus 5. Okay. pOH, I have to do this one in the calculator because we've got a coefficient there. 7 exponent 5, and take the log of that, which is somewhere, here it is, and then change the sign, 4.15. pH is equal to 9.85. Right, that should be, plus those together should be 14. 13. Yeah. Okay. So this one is still the most basic. Let's look at D. Answer D Its pH is 4.2. That's already given to us. All right. At least two of the solutions are equally basic. No, all the numbers are different. There, 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 there. So we can decide which one is the most basic. And the most basic has the highest pH. This one. Okay, that's number 7. All right, number 8. Here we go. Number 8. Which of the following solutions contains the strongest acid? All right. So we have 5 molar HCN, 3.5 molar H2C6 H6O6, and then 2.5 molar acetic acid, 4 molar HOCl, and then 1 molar HF. And each of these has a K value, right? So Ka, one of them has 2 Ks. Can you figure out which one? The one that's got 2 acidic protons. It'll have 2 Ks. The rest of them only have 1 K. So that K, I'm just going to put the powers of 10. For comparison purposes, that's all you need. So this is 10 to the minus 10. This is 10 to the minus 5 and 10 to the minus 12. Acetic acid is 10 to the minus 5. And hypochlorous acid is 10 to the minus 8. And HF is 10 to the minus 4. Oops. 4. There we go. Okay. First thing is this second proton is not going to affect the pH at all. In fact, it has nothing to do, or I should say very little to do, with the strength of the acid. That's the key. The question is, which one is the strongest acid? When we talk about acid strength, we're exclusively focused on Ka. Concentration doesn't mean anything, because Ka tells us what's the tendency of that acid to dissociate one of its protons. So the concentration means nothing for strength of an acid. Now, if we were looking at the pH, the actual acid value, pH or hydrogen ion concentration, yeah, you would need the concentration. But when we're talking about strength, it's all K value. All right, so we really only need to focus on the first K value. For this one, throw that one out. It's 7 orders of magnitude weaker than the first proton, has no effect. All right, so now what we have to do is look at who's got the biggest Ka, right? And -4, it looks like. So E is the strongest acid. By definition, it dissociates to the greatest extent in aqueous solution. All right, that's 8. 1 more to go, and we'll be caught up. And then I can splice this thing into the other review video. There we go. Number 9. Which of the following statements are true? Okay, so we got to look at all of them, because D says at least 2 of the statements are true. E says all of the statements are false. So we got to look at A, B, and C, and determine whether they're true or not. The pH of a strong acid is always lower than the pH of a weak acid. pH of HA strong is always lower than the pH of HA weak. Is that true? Now we're talking about the pH, not just the strength of the acid. We would take into account the strength, right, the K value, but the concentration also has a bearing on the hydrogen ion concentration. So, is this always true? Can you think of a scenario in which it would not be true? Say a strong acid were 0.0001 molar, and the weak acid were 15 molar. In that case, the pH of the weak acid would be much lower than the pH of the strong acid. Right. For instance, let's say 15 molar acetic acid. Right. That's my abbreviation for acetic acid. That's the acetate ion, and there's your proton. Okay. So that was false. How about B? The pH of a solution can never be negative. pH less than 1 can't happen. Really? It's just a calculation, negative log of the hydrogen ion concentration. Can we think of a situation where the hydrogen ion concentration will produce a negative pH value? Yeah, negative log of, let's say, 100 molar. That's too much. Let's be more realistic. Say 10 molar, right? 10 to the first power. So this would be 1 right here, and that would be your negative 1 pH. Now usually when you get below 2 pH or greater than 12 or 13, then the pH doesn't have as much meaning. The hydrogen ion concentration then is the way to describe your solution. pH is for intermediate range there. Okay. So B is false. How about C? If C is not true, then E is true. So let's look at C. A conjugate acid-base pair, say HA, A minus, right? For the dissociation of HA, you have a Ka value. For the reaction of A minus with water, you have a Kb value. Right? So this is saying that if you want to know what the Ka is, then you take the reciprocal of the Kb. Is that true? No, of course it's not. We've already proven that. That's false. That means E is the answer. But what is the actual way to calculate Ka from Kb or vice versa? The relationship is Kw equals Ka times Kb. And we proved that in lecture. Right? That's why pKw equals pKa plus pKb. Right? When you take the log of a product, you get a summation. That's why the plus instead of the multiply. So if this is 14, then the sum of these two always has to be that. So how do we use this to find that? Ka then is this one divided by that one. Or you could say this one is equal to that one divided by that one. Either way works. Because sometimes you need the Kb. So you do a complete titration in which all of the acid is used up. Right? Like you go to the equivalence point. If you go to the equivalence point, then there's no HA left. Right? So what do? Well, after the stoichiometry, you get the equilibrium. Now you got all A minus in water. What is it going to react with? It's going to react, since this is a weak acid, it's going to react with water. Well, there's none of that to react with it. So A minus reacts with water. Now you got a Kb. You knew the Ka at first, but in order to do the equilibrium, you've got to get the Kb for the A minus plus water. Okay, and that's how you do it. All right, that was number 9, and I think we got number 10 already done. So I'll splice this one into the other video and upload them for your viewing pleasure. Okay, let's see, that's a mess. Flip that over. Now it's clean. Okay, das Ende. I forgot to start the recording. So we'll carry on with 10, and then I'll go back and do 1 through 9. Okay, so which one of these matches that scenario? Well, I would look for the one with hydroxyls on the product side, right? That would be C. And then F minus is our conjugate base, right? Leaves us with hydrofluoric acid plus OH minus. That's the best answer. Now, what's another possible answer? Well, the one that immediately comes to mind is the conjugate acid-base pair, like that. So the conjugate base of this pair would be that one. That would react with water. And still give us a hydroxyl. Okay? But that was not in here. It's this one, which is C. Okay? All right. We covered 11 already. 12 is a good one. For which of the following 0.1 molar diprotic acids would the second dissociation affect the pH significantly? I mentioned that a little earlier. The only second dissociation constant that has an impact on the pH of any acid, a diprotic acid, is the one in which the second dissociation is pretty close to the first dissociation. So if they're very close to one another, say within 1 order of magnitude, it will have an impact on the pH. So let's look for one that satisfies that one. A is -2, -7, not too far. B is -4, -8, that's 4 orders of magnitude. C, -4, -9, that's too far away. D, -3, -4. And the -4 is 9.3 times 10 to the -4. I mean, that's less than an order of magnitude, so D would satisfy that condition. And E is false. The second dissociation never affects the pH significantly. It usually does not affect. But never is the key word there. Okay, that was 12. Yes. Knocking my board over. Okay. Let's see here. Okay, let's look at 15. So we dissolve a sodium salt of an acid. Could be anything. The associated acid with this conjugate base, right, is weak. Okay. Dissolve it in water. Don't put anything else in it. Which of these is true? Is that one equal to that one? Or this one equal to that one? See, is this one equal to that one? Or is this one equal to this one? Or none? All right. So when you dissolve that in water, what are the major species? Sodium ions, anion, A-, and water. Those. Sodium's not going to react with water. It's not going to react with this one because they're completely soluble. So the reaction that operates here, I need some room. Let me erase this so I can continue talking without having to erase anything down here. So the reaction that's going to happen is this one plus that one yields this one plus that one. Okay? So we know the concentration of this one because we established it there. At least this initial concentration. So it's going to react with water. So what's the hydrogen ion concentration in that solution? Is it equal to A-? Well, we can also set up an ice table. And I don't have a lot of room, so what if I do it this way? Can I do that without knocking it down? Yeah, we can still see that. So if we have this and this and that, right, and we have initial change in equilibrium, right, we start off with a certain amount of this. None of that, for all intents and purposes. So what's going to happen? We're going to produce some of this, right? And some of that. And we're going to lose it from this side. So the equilibrium situation is going to be this one minus that one. And that one's going to be an X, and that one's going to be an X. Okay, can we say that this one is equal to hydrogen ion concentration? No, because all of it didn't dissociate. I mean, all of it didn't react with water to produce the weak acid. Plus, once we produce that weak acid, it's going to dissociate further. I mean, it's going to, this is our stoichiometry, and then we do the equilibrium, and it's going to come back, right? So we can't say that this one is equal to that one, not based on those calculations. How about this one? Is that one equal to hydroxyl? Well, it was before we added the conjugate base of a weak acid. But once we added the weak acid and it dissociated, now you've got a strong base that's going to react with any hydrogen ions that are there, right? So we're going to, this is false. That actually should be greater than. How about this one? A minus is equal to hydroxyls. Well, that can't be either, right? Because you've got A minus minus X yields X over here. So they can't both be equal. HA equals hydroxyls. That's true, because that is equal to that. So that's our true statement right there. Okay? All right. That was 15. Let's see. If we go till 10:15 on chapter 14, we should be okay, because chapter 14 is the longer chapter. Okay, let's do 17, 18, 19. So we're looking for, what are the characteristics, acidic, basic, neutral, or can't tell, for each of these substances dissolved in water. So for 17, let's dissolve this one in water. And remember the rule of thumb. If we combine a strong base with a strong acid, you get a neutral solution. So sodium hydroxide combined with nitric acid gives us a neutral solution. All right, so 17 would have to be C. Sodium carbonate. Okay. Here we've combined a strong base with a weak acid, right? The weak acid is carbonic acid. That's the one that's important for maintaining pH balance in your body fluids. So a strong base and a weak acid gives you basic solution, which would be B. 19, we're combining a weak base and a weak acid, right? So for that one, you need to know, compare the Ka with the Kb. Okay. So for this one, ammonium acetate, the Ka for this one is 5.6 times 10 to the minus 10. And for this one, the Kb is 5.6 times 10 to the minus 10. Oh, that's an easy one. They're both equal, right? So we get a neutral solution. So we use the Ka for this one and the Kb for this one, which is a competition for water molecules, right? The equal competition. What if this one were 10 to the minus 9 and this one were 10 to the minus 12? Then the Kb would win. It would extract protons from water more strongly than this one could donate them, and we would have a basic solution. The Kb wins. If the Kb wins, it's basic. If the Ka wins, it's acidic. We didn't hammer that one real hard in the lecture, so I wanted to make a point of that one. Compare the Ka with the Kb for this base versus that acid. And the larger one wins, and that reaction dominates. So this reaction is with water to produce hydroxyls, which means you have a basic solution. Okay. Let me look ahead just a second and see if there's anything toward the end that we need to deal with. I don't want to miss getting anything in this chapter that's important. We haven't done any calculations of pH or ions at equilibrium yet. Okay, here's one based on definition. It would be good to review. 21. So you have the salt here. Oh, and that's the wrong one. 22. We're talking about oxoacids or oxyacids. Which is the most important in determining the strength of an oxyacid? Well, what's an oxyacid? One that has oxygen in it, plus some other element, usually a nonmetal, like chlorine or bromine, for example, and then you have so many oxygens associated with it. So the most important factor in determining the strength of an oxyacid is the number of oxygens. This factor right here. So that would be D. That's just based on the data, of course, and by definition. Let's see. This one doesn't have a number. Since we're on that topic and toward the end of that chapter, we had two types of compounds that produce solutions. One was the acidic anhydrides, and the other was the basic anhydrides. Okay. The acidic anhydrides are oxygen-containing compounds of nonmetals. For instance, sulfur dioxide, nitrogen dioxide. I think those were the two examples we gave. The basic anhydrides are oxides of metals like magnesium oxide or calcium oxide or sodium oxide. So what happens when you put them in solution? Well, when you put them in solution, in this case, you transfer these two hydrogens and the oxygen over here, and you get H2SO3, which is an acid. Okay? And that pattern holds for any of the nonmetal oxides that dissolve in water. When you put one of these in solution, what happens is you combining this molecule with that molecule gives you the actual hydroxide of the metal. And you can check for balanced equation, 2 oxygens, 1, 2, 1 magnesium, 2 hydrogens, 2 hydrogens. And that's actually a Arrhenius base because it has a hydroxyl in the molecule. You can do that with any one of these. Okay, let's see. Lewis acids and bases. Right. So let's make the connection with Lowry-Bronsted first. Lowry-Bronsted says what? An acid, let's see. An acid is a proton donor. The base is a proton acceptor. Okay. How about Lewis? Lewis says that in order to donate a proton, the molecule has to accept an electron pair to make that hydrogen positive. So an acid is an electron pair acceptor. And a base, conversely, is an electron pair donor. Okay. So in order to be a Lowry base, the proton has to be accepted, and when you do that, you donate electrons to the proton. So the base then becomes also an electron pair donor. So that's how they're related. The difference is this takes place in aqueous solution. This one is not restricted to aqueous solutions. These types of reactions can occur in non-aqueous solutions, and that's one of the driving forces for Lewis developing that theory and that definition, primarily for organic reactions. There's some organic reactions, if you conduct them in aqueous solution, water is a reactant, and it kind of messes with your with the desired reaction. So you have to conduct those reactions, some of those reactions, in non-aqueous solutions. Okay. So let's look at some of our questions here that pertain to that definition and see if we can apply that knowledge. Okay, well, let's just take 25. Which of the following species cannot act as a Lewis base? All right. Okay, a Lewis base is a proton acceptor, which means it's an electron pair donor. So which one cannot donate electron pair? Well, let's say that one's got lots of electrons to donate, right? So that's a base. That can donate. This could donate. It could be a base. What would that mean? If it donated an electron pair, what would be the result? Something like this. Remember, sulfur is in the same family as oxygen. So you can think of that as analogous to H2O. It can accept a proton. It can donate electrons. That's sort of the analogous hydronium ion. I don't know what you would call it. Sulfonium ion. And this one can donate an electron pair and pick up a hydrogen. Okay. So if you look at it that way, from the Lowry-Bronsted angle, it becomes easier to rationalize these as bases, Lewis bases. This one does not do that. The reason for that is, and this may be hard to understand, is one of the reasons I wanted to do this one, is that methane is not only is it a covalent compound, the carbon is satisfied. Its octet is satisfied. It doesn't want to give up. It doesn't want to receive any protons. And conversely, it doesn't want to do that with electrons either. I'm not explaining it too well. Let me see when I have time to think and write it down, that's the best time. Okay. Look at it in terms of, do they have lone electron pairs that they can donate? Right. So I've already looked at it from the Lowry-Bronsted angle. Let's look at it from the Lewis structure angle. So this would have extra electrons, lone pair electrons to donate. In fact, the oxygen itself has a couple of lone pairs to begin with. Well, that's where that double charge comes from. That has lone pairs. Sulfur has 6. 1, 2, 3, 4, 5. Yeah, 6. 1, 2, 3, 4, 5, 6. It has these 2 electrons. Unpaired electrons, plus these 2 hydrogens are attached here. Right? So it has those 2 lone pairs also. Right? So it's a donor. How about ammonia? Ammonia is like this. It has one lone pair, right? So it's a Lewis base. But methane has no lone pairs. Carbon only has 4 electrons to donate, and they're all tied up in bonds. Right? So it's not a Lewis base. I think that makes more sense when you look at it from the lone pair angle. Do they have any extra electrons that they can give up? And yeah, everybody does except methane. Let's see, that was 25. And I'm running out of time, so I better move along and see. Okay. I have to choose. And let's take 36. This has several steps in it. I'll tell you what. Let's move as far to the top as possible. All right, so what are we given? We're given 10 milliliters of 10.1 molar HCl. Okay? And we want to know how much water plus how much water would equal the same pH as 0.90 molar acetic acid with a Ka of 1.8 times 10 to the minus 5. So if we got to find out how much water to add to this one to make the same pH as this one, we got to find out what the pH of this one is. Then the hydrogen ion concentration would be equal to the concentration of HCl because that's a strong acid. So we need to work backwards. We need to find out what's the pH of this one. Okay. So this reaction is going to be acetic acid, right? And it produces hydrogen ions and acetate ions, right? So what do we have initially? Initially, we have 0.9 molar HOAC, 0.9 molar. And we approximately 0 there and definitely 0 there. But since remember the competing reaction from that for now, these are not the same in the same solution. It's this one and then saying, what do you have to do to make this one? Right, so two different solutions. But the only competing reaction in here is water. And with 10 to the minus 14th, there's no competition. So that's why we can say this is virtually zero. So what's going to change? The reaction is going to go that way. Right. So we're going to have this and that minus a certain amount of that. Minus X, and then X, and X. Okay? So what's our expression? This is equal to X squared, because it's that one times that one, over this one. Right? And that's approximately equal to this one. So we need to multiply that times this and take square root of it to find out what X is. And then take the square root. There we go. So X is 4.02 times 10 to the minus 3 molar. All right. So that's our target. We want this concentration for that solution. All right. So in order to do that, we have to erase all this. And remember how to do dilutions? All right. M1V1 equals M2V2. So the molarity of that solution is 10.1 molar. And the volume is 10 milliliters. And remember I said the molarity, the concentration of hydrogen ions is going to be equal to that. Right? So we can use that in here because they're 1-to-1 ratio. And we've determined what the hydrogen ion concentration is here. Well, actually, we don't. Let's see. Yeah. So this is the molarity that we're shooting for, that one right there. And that's the final volume. All right, so if this is the final volume, divide this into that. That's 2509 milliliters. That's the final volume. So we subtract that from that one. And it's minus 10. So that's how much we have to add to that one. Did I get that right? How come I got it wrong? Did I write the right numbers in there? I wrote the wrong numbers. It's 11.1 molar. So that would be 11.1. Let's do that again. There we go. Now this is 276.22. No, I did that wrong. Let's do it again. No, I did it right.
Did you change your volume to liters?
Well, I shouldn't have to, but maybe I better. Let's do it this way. We want a concentration of 11.1 molar. And to get that, we need moles of hydrogen ions, right? Which is moles of hydrogen ions, which is determined here, which is 0.010 liters times 11.1. That's not right. That's 4.02 times 10 third. That's what we're shooting for. And we get it by moles divided by volume. Right? And on the bottom, we need volume. And volume would be 0.010 liters plus some X amount. There we go. Now we can solve for X, because X is the amount you have to add to it. Right. And to save time, X should be 27.6 liters. Okay, I think we need to get on to chapter 15 before I talk us into a corner. I'm going to have to go back and do 1 through 9 anyway. Did I miss anything in there that you need to cover? If not, we'll move on. Chapter 15 is essentially buffers. Okay, let's see how many we have to deal with here. 25, so we have fewer to pick from. All right. Well, let's just start with 1. Right? For a solution that's equimolar in HCN, and sodium cyanide, we're looking for the false statements. Which statement is false? So from the choices we have, it looks like only one of them is false. Is this a common ion effect? The first thing I recognize about this combination, if our solution is equal amounts of this and that tells me we have a buffer, because you've got the conjugate base of the acid in equal amounts. And remember from the Henderson-Hasselbalch equation, if you have that ratio equal to 1, then the pH equals the pKa. So we're right in the middle of the buffer region. And when you're talking about buffers, you're always talking about common ions, the common ion effect. So that one's true. The hydrogen ion concentration is larger than it would be if only the HCN was in solution. This is larger than HCN alone. Is that true? No way. Remember when we did our titration curve? pH added base. Where did we start with our acid? We started down here, right? So if it's just this one alone, once you get to this point where you're in the buffer zone, the pH is higher. Well, the hydrogen ion concentration is lower than that one alone. That's false. And that's it. We found our answer. Let me see if we need to look at the others. The hydrogen ion concentration is equal to the Ka? Yes, it is. That's how you identify, or that's how your lab experiment allows you to determine the Ka of acetic acid when you do the titration. You look for that point in the curve, right in the smack dab middle of the buffer zone, which is half equivalence. Find out how much volume is equivalence, come back to half of that, and that point on the curve read over to the pH, which is equal to the pKa. Then you do the log, anti-log conversion and find the Ka. But what that means is the hydrogen ion concentration at that point is equal to the Ka. So C is true. Addition of more of this will shift the acid dissociation equilibrium to the left. Let's see if that's true. If you add more of that, what's it going to do to that reaction? You're adding this common ion, shifts it back this way. That's true. And in so doing, it consumes some hydrogen ions and produces this weak acid, right? Because this is a strong base. It's going to pick up any free protons, or actually it's going to steal them from hydronium. And E, addition of sodium hydroxide will increase the cyanide ion and decrease that. So if we add sodium hydroxide and nothing else, you're adding hydroxide, which consumes protons, shifts the reaction that way, and makes more cyanide and decreases this. So what these statements are doing is actually describing various characteristics of a buffered solution. What ifs in a buffer? Okay. Oh, 2's good. And you recognize a buffer. Which of the following mixtures would result in a buffered solution? So E says at least 2 of the above would be a buffer. So we got to look at all of them. So what if we mix 100 milliliters of 0.1 molar HCl and 100 milliliters of 0.1 molar sodium hydroxide? That doesn't matter. This matters. Strong acid, strong base, it doesn't matter how much. If you add the same amount of them, you've neutralized them. You don't have a buffer. You've got a neutral solution. So that's not a buffer. So how do we tell a buffer? Well, we need either a weak acid, which is in most cases is true, or a weak base. So the next one is definitely a weak base, ammonia, combined with sodium hydroxide. Well, you can't combine a weak base with a strong base and get a buffer. If you're going to use a weak base, you've got to use an acid to make a buffer. So B's false. C, you mix hydrochloric acid with ammonia. Okay, that could be because you got an acid and a base. So let's see what happens. If we have 100 milliliters of 0.1 molar hydrochloric acid and 100 milliliters of 0.1 molar ammonia. What do you have there? You've got equivalence. You've got exactly the amount of this acid as base. You're not here, you're here. You've neutralized it. That's the stoichiometry. A perfect stoichiometry. All right, so that one's false also. D. If you mix 50 milliliters of 0.1 molar HCl and 100 milliliters of 0.1 molar ammonia. Aha! Now where are we? We're at half equivalence. We've only neutralized half of this one. That puts us right there. This is full here. This is 1/2 there. That's our buffer. D. So E can't be right because only one of them is true. All right. Before we get too far along, we need to do some calculations. Let's see on our way there if I find anything that really sticks out. Number 7. All right. Which of the following solutions will be the best buffer at pH 9.26? So our target is 9.26.
Here's the website about you making $10,000 weekly. Go to
okay, so what do we know about how to choose a buffer? If our target is 9.26, the best place for a buffer is where the pH equals the pKa. And then this part of the expression is that ratio. And if we make those equal, then this goes away. And that's the perfect right dead center in the buffer region. So we're looking for a pH equal to pKa for the weak acid or the weak base. All right. So let me keep myself on track here. I don't want to wander. Let's see, get back to 7. So we have 2 conditions to meet. One is the pKa, and the other is the acid-base ratio. So we can eliminate some of these. Well, A is definitely a buffer because it's 0.1 molar acetic acid and 0.1 molar sodium acetate. Right. So you've got equal amounts. You've got equal amounts of that anion and this acid, conjugate base with acid. So that is a buffer. But is it at the right pH? Well, no. Right? All you have to do is take the Ka of this acid at 1.8 times 10 to the minus 5, take the negative log of it, and you end up with something in the neighborhood of 4.8, I think, something like that. 4.74. Right. So that's a buffer, but it's in the wrong spot. So B can't be it either. Even if it is a buffer, it doesn't work because it's got the wrong pKa. Right? So B is false also. That's wrong. That's wrong. So our only choice is to use the ammonia. Right? So will the ammonia work? Well, let's see. The pKb for ammonia is also this. Right? But this would be the POH. Right? If we calculated that, it would be the POH for a pKb. So if we subtract that from 14, then we get, let's see, 9.26. It's right on target. So if we use ammonia and as the base and ammonium as the acid, then we just need to look for the right concentrations. And let's see which one would work. Let's look at the question. Which of the following solutions would be the best buffer? Best. Right? Best refers to what's the buffer capacity. Which one can stand the most addition of acid or base? Right? So that's what had me puzzled, because C is definitely an ammonium buffer because it's 0.1 molar of that and 0.1 molar of that. Right. So that satisfies. But D is 5 molar of each one of those. So it has a higher buffer capacity, but the ratio is right. So they're both buffers, but D's better. And then E can't work at all. Right? E is just stupid because you've got a weak acid and the wrong weak base. I mean, you don't have the conjugate base for the acid, or you don't have the conjugate acid for the base, right? So that one can't work. So it's a competition between C and D, and since the buffer capacity for D is higher, it's the better buffer. I need a sturdier easel. That's what I get for buying cheap. Okay. So before we run out of time, let's find a reaction that needs to be accomplished. An equilibrium that needs to be calculated. Well, What about this one? Yeah, that would work. Let me see if there's a better one. Lenny? That would work. Let's see if I can make sense of 20. Okay. So here we have an indicator problem. So we look for an indicator. Assume an indicator works best when the equivalence point of a titration comes in the middle of the indicator range. Okay, where is the middle of the indicator range? The middle of the indicator range has the indicator's pK in that middle, right? So we said, based on physiology, the range of an indicator is plus or minus 1 unit from the pKa. pH of pKa plus or minus 1. So we need to find out what is the pH at equivalence for the following titration. So our titration is this one, molar, hypochlorous acid, and the Ka is 3.5 times 10 to the minus 8. And that's titrated with strong base. Okay, so we need to find out what's the pH at equivalence. All right. So, at the equivalence point, what will be the major species that are present? Right. So if we do the stoichiometry, we're going to have this one plus this one yields. I only need a single arrow for stoichiometry. Would be sodium hypochlorite and water, right? Bleach. That's what that is. But this is soluble in water, right? So once we've neutralized it, we've changed all of this to that, which means now we have this and this and that. Right? So that becomes our equilibrium species. This one's not going to react. It's kaput. It's a spectator. So now we have this one in water. So now we're going to do this one plus water yields this one plus OH. Okay. Now we're not talking about Ka anymore. We're talking about Kb. Right? So to do the calculation here, we need to know what Kb is. So it's 1 times 10 to the minus 14th divided by 3.5 times 10 to the minus 8, which is 2.86 times 10 to the minus 7. 2.86 times 10 to the minus 7. Okay. So now, what's our initial concentration of this? Well, how many moles? If we have equal volumes here, once you've neutralized all of them, then all of the volume there is converted. Are we given, excuse me. No, we're not given a volume. But the volume is going to be equal because you have the same concentration, right? So it's going to take the same volume of this one and this one. And we can go with, now we're going to have all of this converted to that. So that's our concentration for this one. Water doesn't count. And we're going to say that's 0 and that's 0. So now we're going to have that. 0.1 minus x, and then x and x. Okay. So now our expression is going to be we've already done that one, so we can erase that. Now our expression is going to be the Kb is this value, and it's this one times this one over, which is approximately equal to, okay, so 0.1 times this one means that x is the square root of 2.86 times 10 to the minus 8. Because we multiplied it times a 10th. Okay, and the square root. So I get 1.69 times 10 to the minus 4 molar. All right, so that's the concentration of hydroxyls. The question was, which indicator would be the best? So these indicators are given in terms of their pHs can be interpreted in terms of pKa. So if we have pOH, we need pH. Right? So we need to take this one, convert it to pOH, right? Negative log of that one. pOH equals 2.76, and then the pH is that subtracted from 14. 11.2. So 11.2 is our target pH, and we look for the one that fits that, and Phenolphthalein inches up, but thymolphthalein is closer because it's 10.5 is closer to 11.2. So that should be D. Okay. Let's see. Let's see if we've got any here that we haven't used the Henderson-Hasselbalch yet. So what conditions, under what conditions can you use Henderson-Hasselbalch? Okay, let's just write it first. pH equals pKa. So if you're dealing with a reaction that's got pKb, you got to convert it to pKa before you can use Henderson-Hasselbalch. Like if you're doing an ammonia reaction, you're going to have a pKb, so you got to convert it to pKa and use the acid in its proper place, in the denominator, in the base, ammonia, in the numerator. It's just a side point. So we have the conjugate base and the acid, right? So that's Henderson-Hasselbalch. So what does this mean? This means equilibrium. Now, if you're in the buffer region, if you actually have concentrations here that put your solution in the buffer zone, you can use initial values for these. Okay, and if you're outside the buffer zone, then it's not much use for doing calculations, unless you're able to determine the equilibrium concentrations of these factors. If you can do that, then you can go outside the buffer zone, and you'll be perfectly all right with your calculations. So, circumstances where you can use this directly. If you're given concentrations of the acid, I don't know, maybe something like that, and the conjugate base, right, this will be added directly. This will be added with a counter ion, like something like that. If you're given that concentration, and it's equal to, well, I don't know, maybe 0.25. You're still close enough. So you could just plug those values in here. If you have the pKa of that acid, then you could determine directly, like that. If these values are way far apart, like if this is 0.05 and this is 0.3, then they're a little far apart, and you need to do the stoichiometry followed by the equilibrium to find out what those values are. And then you can either do the calculation straight out from your equilibrium results, or you could stick the values into the pK. All right, so let's see if we can find an example to work from. Let's see. '23, that's a good one. I'm going to leave that up there. Maybe we can use it. Okay, so we're given 50 milliliters of 0.2 0.0350 molar hydrocyanic acid. And its Ka is equal to 6.2 times 10 to the minus 10. Okay? And we titrate that with we titrate it with 0.0333 molar sodium hydroxide, and it wants to know what's the pH after 15 milliliters of this is added. Okay. So the first step is stoichiometry. What's the reaction? We got HCN, sodium hydroxide, and that gives us, of course, water plus sodium cyanide. Okay. So we've got 50 milliliters here times concentration of 0.0350 molar, which is equal to 1.75 millimoles. Did I explain millimoles before? Milliliters times molarity is millimoles. And millimoles divided by milliliters is molarity. Okay. And then for this one, we've got 15 milliliters times 0.0333 molar, which is equal to 0.4995 millimoles. Okay? So that's before the reaction. After the reaction, we have used up all of this, right? Stoichiometry, that which one runs out first, right? That one runs out first. So for this concentration, we have 1.75 minus 0.4995, which is equal to 1.25 millimoles. So that's our starting point for the equilibrium in this concentration here. And our starting point for that one, because this one drops to 0, and this one then becomes this one then becomes 0.4995 millimoles. Okay, so that's where we start with the next reaction. Let's see. But look here. We don't have any more sodium hydroxide there, no more hydroxides from this source, but we still have some of this. So the reaction is still going to be this one producing that one. It reacts with water, or it dissociates and produces hydrogen ions. So in that case, we need to keep these concentrations, and let's see, I don't need this space, so let's do that. And we're still going to have this reaction producing that plus that, and the initial concentration here is 1.25 millimoles divided by, what's the total volume? 15 plus 50 is 65 milliliters, and the total volume here is the same volume, but the concentration is different, divided by 65. So the initial concentration there is 1.25 and 65 is, did I do that right? 15? Yes. Is 1.92 times 10 to the minus 2 molar. And this one is 7.68 times 10 to the minus 3 molar. Okay, now we have our starting points for the equilibrium. Okay, so what's going to happen? Well, we can tell from this concentration is much larger than that concentration. So since it's a 1-to-1 reaction, we don't need to calculate Q. We know that, well, also based upon the fact that that's 0, because we did the stoichiometry and now we're doing the equilibrium, that 0 is going to go that way, which means the change is going to be minus something here, plus there, plus there. This is going to be X. This is going to be 7.68 times 10 to the minus 3 plus X. And this is going to be 1.92 times 10 to the minus 2 minus X. So now we need our equilibrium expression, which can be equilibrated to this because we're still talking about the acid, right? So it's 6.2 times 10 to the minus 10 equals that times this. I'm running out of juice here. Divided by this. Minus X. Now, I don't think we can make an approximation because look how small that value is. X is going to be a significant amount of that. So we're going to have to solve this quadratically. And it's already been done in the homework. And if I did my calculations correctly, X is equal to hydrogen ion concentration. So once we solve for X, we know what that value is and can calculate the pH. 1.55 times 10 to the minus 9. Well, actually, having done it quadratically already, it is going to be a small value compared to that. So technically, we should be able to do the calculation without that X and end up with pretty close to that value. But then the pH is going to be the negative log of that, which is 8.81 pH. Okay, does that answer the question? Yes, it does. Okay. So that took us a while to get where we were going. 24 is similar. Let's see, are there any glitches in there? No. 24 is just an example where you use a KB reaction. Did I draw the structure out for you? KB for ethanol amine. Okay, I didn't. That's why in the description, I actually told you what the ethanol amine looked like. Otherwise, you'd be kind of lost. Ethanol amine is an organic compound. But it has a pK value that makes its buffer zone basic because it has, let's do it the other way. Everybody knows what ethanol is, right? CH3, CH2, OH right there. And then we have on this side, we have the amine group. So actually, ethanol amine has two pK values, one for that hydrogen, one for this hydrogen. And if you are interested in organic chemistry and then biochemistry, you get a snoot full of that stuff. Okay. Let's see. So let's see, where was I? 24. Yeah, 24 ethanol amine. So what happens in these reactions? Well, for this reaction, that's an acidic proton. It drops off, attaches to water. This is a basic group, so it adds a proton from water. Right? So this is going to be the base side reaction. This is going to be acid side reaction. You get that type of duality in amino acids too, right? Amino acids have this central carbon, and then they have some group out here, and then they have the amine group and the carboxylic acid group. Right? So amino acids also have that duality. There's a pKa for this one and a pKb for that one. Okay. So 24 is just, you just need to know that structure. Uh, 10 more minutes. What if we do that last one? Okay, so 25 says that you have an indicator. All right, so this is our acid, this indicator body, and there's our acidic proton. And during the reaction, the indicator is going to undergo this type of reaction. Right? So the color here is going to be different than the color there. That's why it's an indicator. The pKa for this reaction is 9. And the color change becomes visible when (7% dissociation. Which means 7% of this becomes that. Okay. At what pH is this color change visible? So this 7% means in decimal ratio, it's 0.07. And that number is equal to the ratio of this to that. That look familiar? That's our ratio in the Henderson-Hasselbalch equation. So if we plug that ratio into the Henderson-Hasselbalch, we can find out what the pH is, because the pKa is 9, and then the log of this value is 0.07. So if we solve that equation, we find out that the color change takes place at 7.85. Yep. So what that tells me is this is the bottom end of the color change, of the range. 7.85, 9's in the middle, and probably 10.2 on the other end. So there's your range. That's the actual range. Before we talked about rule of thumb, right? Plus or minus 1. Well, this is plus a little more than 1, and this is minus a little more than 1, where you can see the color change. Okay. So anything else, anything I didn't cover that we need to talk about? Maybe something popped into your head in the last 2 hours. What do you want to talk about the lab? We can do that. Let me get this stuff out of the way.
Okay.
Let's see, match them up. That's 15. That's 14. 15. Put this over here. And I'll flip over to kinetics. I'll just leave it in here. Before we do that, we take a short bathroom break. I'll be right back. Sit down. Let me sit down. There's your treat. There you go. Wish it was that easy for me. Give me a treat and I'm good for another hour. Okay. Where do we start? Where do we begin? Let me add a visual aid here. We're talking about, it's at lab number 2, isn't it?
Yeah.
Lab number 2, chemical kinetics. Okay. I think I need another marker. Get what you pay for. These are cheap. Okay. All right. So what seems to be the problem? Are there any problems?
Okay. For part 2 on activity 2, I think, it says calculate the molarity of the sodium hypochlorite solution. And you told me there's just one answer. How would you calculate that?
Okay. Actually, this is a dimensional analysis problem. Right. You remember that?
Oh, so
Yeah.
yeah.
So you got your starting point. Let's see. 6%. So if you say it's 6%, what does that mean? Well, it tells you that percent, since percent is dimensionless number, you have to know whether it's mass, volume, or volume. And in this case, it said M over V, mass volume, which means 6% is that many grams per 100 milliliters, right? Parts per 100. Okay, so that's where you start. And we're headed for molarity down there, which will be moles per liter, right? Moles per liter. So we got 2 units to convert. The simplest one is to do the milliliters first. If we want liters on the bottom and 10 to the third milliliters on the top, that way these two cancel. So volume's taken care of. Now we need to do grams. Grams to moles, right? So you have the sodium hypochlorite is molecule. So we need to know what is the molar mass of sodium hypochlorite? You know what?
Exact 75.
Hold on a second.
Okay.
You know, I don't think we need the density. The only way you would need density is if it were volume.
Oh, okay.
So that's kind of a trick. If it's mass volume, then it's this way.
Oh,
If it's volume, then you would have volume here, 6 grams of
right.
solution that you would have to convert to
Right.
grams of solution and then go from there. So actually,
Right.
this is simpler. So now we can convert grams
It's
to moles. So we just need to know the molar mass of sodium hypochlorite. Let's see, sodium is 23.0.
yeah.
Oxygen is 16. Chlorine is 35.45. 74.45.
Yeah.
There we go. So that gives us moles per liter.
Mm-hmm.
So let's see what that is. Let's see, 6, convert, divide, and then 1,000 times and 100 divide. So I get 0.806 molar.
Okay. Yeah. That's what I got. Okay. I was just confused if it's something to do with the experiment itself since it's part 2. So I was like,
Oh, okay. You know why we have to do that? Because
why?
when you add so many drops of this bleach to your reaction vessel for full strength,
Right.
you just add that to the dye, full strength.
Right.
Half strength, you would add half the number of drops.
Oh, okay, gotcha. That's why.
You add the other half is sodium chloride. Because
That would make sense for the trail too.
yeah, and
That's why. Okay.
so you also need that concentration for your sodium chloride for the dilution.
Right.
But I think
Okay.
we actually used a different concentration for sodium chloride. It wasn't much different than that.
Mm-hmm.
I give it to you in the data sheet, I think. I hope I do. Or maybe I gave it to you in the talk. Shoot. Ah, here it is. 0.878 molar sodium hypochlorite.
Oh yeah. Yeah, it was in the sheet at the very first
Yeah.
under materials, I think.
The reason it's different is because
Mm-hmm.
this is calculated as mass volume, and 878 is calculated as mass.
Okay.
So you have to use the density, and the density bumps it up some. Instead of water 1 mil per 1 gram per milliliter, it's 1.01.
Yeah.
That's the difference.
Okay. All right.
Everything else look good?
Yeah. Yeah. Just
All
that
right.
one. All right. Thank you.
Okay, take it easy, and I'm gonna go back and re-record 1 through 9 because I missed recording earlier. That's part of
All
it.
right.
And I'll just splice them in the proper order.
Okay.
Okay, see you later.